So we're going to talk about inconsistent linear systems, projections, and least squares. So you guys, especially you science types, have done a lot of stuff using least squares plots for various things. Of course, now it's all done on calculators. You don't have to know how to do it by hand, but I'm going to explain to you where it all comes from. So I'm going to put an equation on the board. Here's a very innocent-looking matrix. Columns are 1, 1, 1, 2, negative 1, 1, and I want you to solve the equation that that matrix times x is the vector b, where b is that vector. So how would we do this if we were back a few chapters earlier? And then what do I do? Row operations. Go on, dictate.
1, 2, 1, 0, 1, 0.
What? What? 0,
Negative 3.
Negative 2. Negative 2.
Nick, you're fired.
Oh, jeez.
0, negative 1.
Now what?
Switch the second, third.
I'm going to switch second and third. Okay. And then I add 3 times this to that. Unless I screwed up.
No.
I think that's right.
Well, what do you say?
Unsolvable.
Inconsistent.
Impossible.
Now, let me just point out that if you were trying to fit data points to some sort of equation, say an equation of the form y equals ax plus c, and I'm using c instead of mx plus b here for reasons that you'll see. That turns, you may not have thought about it, but for example, you might have data points like negative 2, 1. So this is the kind of thing back in my high school days doing chemistry and physics labs. We would always have to do measurements and then plot things on graph paper or log paper. This was before we had calculators that computed things for us. And so you might plot these data points, and for whatever reason, whatever theoretical reason, they're supposed to actually lie on a line. Now, I know Dan well enough to know what he did.
What did I do? Just kind of.
You fudged the points to make them be on a line.
Whoa, whoa! That was not me. Hold up.
We don't.
You maximize the sum of squares.
So the idea you're trying to do here is you're trying to find some line, say like that may or may not be correct, that is sort of optimal in some sense, but it fits this sort of framework, because if you're trying to fit data points to a line, what are you trying to do? If you're trying to fit to this equation, having, say, let me actually label these points here. Say this is negative 2, 1, and this is 0, 1, and this is 1, 3, and this is 2, 2. If you actually have those actual numerical data points you're trying to fit, you would want to say, well, if they satisfy this equation, then I would have y equals a times x plus c. That's for the first point. And then for the second point, I would have y. Wait, I did it backwards. y is 1, and x is -2, sorry. I've been on vacation too. Right? This is x, this is y. All right, so for the second equation it would be what? A times,
7.
and the third?
8 times. Oh, we're doing that one.
And then,
8
times
times 1 equals 3.
so this looks like a system of 4 linear equations in 2 variables. And so this would turn into an equation that looked like, your variables are a and c, and then you would have, your right-hand side would look like this, and your left-hand side would look like that. And is this equation consistent?
Yeah.
I'm pretty sure these 4 points do not lie on a line.
Really?
I think you guys can probably give me a proof.
Probably.
Right, so this is inconsistent as well. The question is, what is the best way to try to solve an equation that's inconsistent? So, what is the best fake solution of an equation that has no solutions? Reminding you guys about evaluations of an inconsistent system. So what does it mean that the system is inconsistent? If you have ax equals b, and you're saying it's inconsistent, let's review back from chapter 4 what that means.
There's no x, or,
There's no x,
so that ax equals.
but is there some picture I could draw here that relates b to something?
Is it
What?
one of the rows you get
So
0?
let's say a, and I'm gonna confuse you today. I'm gonna call a to be an n by m. I'm gonna switch it. I never know which way to do it, but I'm gonna switch it for fun.
You were-
Matrix.
didn't know which way.
So where does b live then?
Rn.
In the M.
R.
N. N.
No, M.
N.
It's mapping to
N.
n.
Q.
And
Q wins. Right? If a is n by m, that means n rows, m columns, so b has n entries. So can you draw, is there some picture relating in Rn that says what inconsistency means?
It means B is not in the span of the column.
Right, exactly. So you look in Rn at the column space of A. Nice subspace. And consistency is the statement that B is in the column space, and inconsistency is the statement that B is not in the column space. So what do you think we should do if we want to find the best, the closest we can do to solving this?
minimize the distance.
So what you should do is project, we don't know how to do this yet, but this is what we're going to learn how to do the next few days. We should find the point in the column space that is blank to B,
Or thought.
Closest.
closest. That vector in the column space that's closest to B is going to be what we call the projection of B into that subspace. So I'm actually going to give you official definitions now. So this is called the projection. So what we did in chapter 1 was projecting a vector on a vector. Remember, we did that stuff way back in section 2. Now we're going to project a vector on a subspace.
Interesting.
Any questions so far?
How do you do that?
No? So, given a subspace, now you probably see why I switched the dimensions of the matrix around so that we're going to have a subspace in Rn rather than Rm. Given a subspace and an X in Rn, proj sub V of X, that's going to be the projection of X onto V, is characterized by what? So this is, I guess I should call this a definition, is the unique vector, so let's call this P for projection. With what properties? What should that red vector have said about it in order for it to qualify as our best possible vector?
P is in V and
First of all, it should be in V. And what should say it's closest?
the absolute value of like V minus X is less than any other, like if V, it's something in V, any vector in V.
Right, so what Matthias is saying is if you imagine picking different red vectors, the discrepancy vector, the error vector, gets longer. What geometric, so rather than mess with the boards, I'll draw the picture again. So now this is called X for no particularly good reason. Maybe I shouldn't call it X. Should we just stick with B? We'll stick with B, it's okay. Okay, sorry. So it's still B.
There's another.
So if I took a different candidate for P, say P prime, what would be, now my picture looks sort of strange, but it's just because it's a picture. What should be the case if this vector here is supposed to be shorter than this vector here? Okay, so you guys are saying stuff that we should have B minus P is strictly less than magnitude B minus P prime for all other P primes not equal to P in the subspace V. But is there a geometric characterization of that, say, thinking about this triangle, say? What can you say that would guarantee that this is shortest?
It's orthogonal to the column space.
If you knew that this was a right angle, no matter what P prime you picked, that this vector was always orthogonal to this vector, B minus P, that would say that the corresponding length there would be the hypotenuse of a right triangle of whom B minus P is a leg.
Right.
Got it?
Yeah.
And that would say the hypotenuse would be longer. So what should we say? The error vector, B minus P, should be what?
Orthogonal to the column.
What's the notation for orthogonal to the subspace? It's in the curve. So what I'm claiming here is that the second condition tells us that B minus P is orthogonal to P prime minus P for all, for all P prime in V. And so by the Pythagorean theorem, And you can write it out from dot product stuff, but the Pythagorean theorem tells us that for p prime not equal to p, the hypotenuse, the magnitude b minus p prime, is strictly greater than the leg of the triangle, which is b minus p. Okay, so does that make sense to everybody? Yes, no? The question now is how do we find, whoops, how do we find p?
Minimize something in space.
So you could do it as a max-min problem, and I will do that for you, but I've tried to set it up for you in terms of a linear algebra problem. So we'll derive this two ways. I don't know that I'll do them both today, but there's two approaches. One using just linear algebra, and one solving a minimum problem. So there's the calculus, of course. But what's the linear algebra supposed to be? How do we say, let's go back to our original equation where V is the column space. Now, so we had an original equation that we were trying to solve where this was the column space of a matrix A. Is that in fact the general situation? If I give you a general subspace, can you always represent it as the column space of some matrix?
Yes.
Yeah.
How?
You can take the basis and create a matrix out of those vectors.
So this can always be arranged by making a basis for V be the columns of your matrix. By sticking basis vectors of V in as the columns of A. Okay, so we could always start off assuming we're really trying to solve some inconsistent system of equations and make the matrix to be the basis for the subspace. So with V equals CA, what does it mean to say P belongs to V? What's that equivalent to saying if V is the column space?
He's in the column space.
He's in the span of the column.
Right, but what's
It's a linear combination.
Oh.
it's a linear combination of the columns of A. How do I write that?
P
There's-
equals AX.
P equals AX. So P is A, and I'll call it X bar for some X bar. The bar is suggesting statistics notation that it's the least squares solution. That's why I'm using it. It's sort of a pain to write. And that would be an Rm. Right? So if a vector is in the column space, that means it's of the form matrix times some vector. What's the second condition? E minus P is in V perp is what statement?
AX equals A minus B minus
Well,
B.
it's in the null space of the transpose.
Null space of whom?
Transpose.
A transpose. Remember, the perp of the column space is the left null space. Remember, that's where the constraint equations came from. Well, this is pretty nifty. That means you have this equation right? To be in the null space of somebody means when I stick the vector in, multiply by the matrix, I get 0. I do not want to erase my original problem. I don't even want to erase that one. I'm running out of room. So what we have is what, yet again, abuse of mathematical terminology. The normal equations. And I honestly don't know who named them this. So it can be coming from normal in the sense of orthogonality. It can also be coming from normal in the sense of statistics. And I don't know who named it. But what do we want to solve? The least squares solution. This is called the least squares solution of AX equals B is a solution of the, as I'm saying, of the normal equations. And what does that equation say? It says A transpose AX equals A transpose B. All right? You put the A transpose B on the other side of that equation, that's what you have. And that's what's called the normal equations. Now, somebody ought to think to ask, how do I know this equation is consistent? Any ideas? So why is this important equation consistent? And you didn't complain at me, but I was inconsistent with my syntax in this sentence. Read the sentence and tell me what you now notice.
Which sense?
Least square solutions is?
The equation is a solution.
No, that says solution.
Okay.
The is okay.
Is it the solution
I said the,
Least
and then I said
A.
hey. Did that not bother you?
No.
No.
Are you all going to tell me you get C's in English?
The.
Not yet. 60 times.
So, what would say that this equation is not only consistent, but in fact has a unique solution?
Oh, it's ATA, it's
Non-singular.
not singular.
So A transpose A will be non-singular if what's true? Yeah, but you've done homework. You've forgotten it, but you've done homework on this in the past few weeks.
If A transpose AX equals 0, that's not true.
Sure, that's not the last few weeks. If the columns of A are linearly independent,
Right.
this is always a non-singular matrix.
But we made it that way.
Well, we didn't make it that way here,
Oh, okay.
but we made it that way when I was setting up the general problem.
Yeah.
So this will be non-singular whenever the rank of A is the number of columns, which is m. And you actually proved this in homework. But you actually proved more, even if the rank is less than m. Indeed, even if the rank of A is less than m, you proved in homework that what would it mean, what would you need to know that this is consistent? You would need to know that this vector is in the
Columns thing.
and the other vector is in the column space of A transpose.
So it's a subset.
They're gonna be this.
Yeah, it
They're
was.
equal to each other.
That was
Well, what did you do?
It's equal if m equals n. I think.
A, B
It's equal
is a
if A
subset
is-
of A.
If A is
Yeah.
You proved that these are equal in exercise 15C.
Oh, yeah.
Even without the rank condition. You showed, when you did this homework problem, you showed those are always the same.
right.
You showed one was contained in the other and that they have the same dimension. So in fact, you're always guaranteed, even without the rank condition, you're always guaranteed that this is consistent, but then there may not be a unique solution. The least squares solution, by convention, not by convention, is the solution of smallest length. Now you will recall, remember we had these pictures where we talked about, and some of you were fond of using this in your homework even. Mallory was, and I've forgotten who else was. Remember the set of solutions of, so this is back now in Rm, so let me draw it here. In Rm, you have the null space let's see, do I want A? No, I want A transpose A. Then the set of solutions to a particular inhomogeneous equation is parallel to that. Solutions, that chalk is just not going to cut it. Solutions of A transpose A X equals A transpose B. How do you find the one that's of shortest length? If you have a translated subspace, how do you find the shortest vector in it?
Perpendicular. The cross product.
Not cross product, we're in Rm.
Never mind.
I take the perp, and where it intersects, it gives me the shortest vector. What's the perp of a null space? It's the row space. So you find this, the vector of smallest length is the vector that's a solution that's also in the row space of the matrix. That's what's called conventionally the least square solution. But any problem you guys are going to do in this course, there will be a unique one, so you don't have to worry about this. Sir?
Is A still n by m?
Yes.
Okay.
So, having derived this equation, what I propose that we do now is solve our two problems. Okay? So I apologize for the scattered board work here. But, so let's solve this one. So let's solve the two problems. Solutions of two example problems. All right, so what do I do? Well, this is automatic pilot. There's, you just compute what that system of equations is and you solve it. So here's A, here's B. What's A transpose B? Now, you could sit there and transpose A like that, and then multiply it by B. And I'm allowing you to do that, but let's see what we get when we do this.
5, 8.
Could you have gotten that 5, 8 without my writing this down?
Yes.
Well, I mean,
You kind of turn your head sideways.
Without turning your head?
You
You do.
What did you do when you computed this 5?
just do the
It's the
second
dot product.
row.
The dot product of?
The row with the row, or column with the column, whatever.
So if you
That
had
one
just
with that
dotted
one.
this vector,
Thank you.
this vector, you would have had the 5, right?
Right.
And if you dotted this vector, that vector, you would have had the 8.
Sure. Column.
So inspired by that shortcut, can you tell me what A transpose A is going to be without writing it all out?
Yes.
3,
All right, I'll write it out, but not, I won't do it in the next step.
Oh, yeah.
3, 6.
3, 6,
Sure.
6.
It's like squaring it. That one, that with that one, that one,
Three.
that one, that one, that with that one. That with that.
6.
Where's 6?
Nowhere.
Oh, it's in the bottom right.
What goes in the off diagonal?
2 and 2.
Do you also remember from chapter 1 doing an exercise that this is always a symmetric matrix?
Yes.
No, but you did.
I do now.
So it's always a symmetric matrix, and so I'm doing the length squared of the first column, the length squared of the second column, and this is the dot product of the columns.
Good.
So what's the least squares solution? I need, well, this is a 2 by 2. What's the easiest way to solve a 2 by 2 system?
Make it a 1 by 4. Or 4 by 1. Whichever one is. You just. No?
What's the easiest way to solve this equation?
Write it as 2 equations.
Not row operations. If it were 5 by 5, of course row operations.
Just write it as 2 equations and solve it
Oh,
normally.
take the inverse.
Use the inverse.
Yeah.
By the way, the inverse of a matrix is on this test.
Sure.
I don't know if I like the inverse though.
Okay, we'll
Well,
take it off then.
so for a 2 by 2, we don't have to do the super augmented matrix. What do?
Divide by the determinant.
Yeah, you
Switch along the.
first you
yeah,
have to find the determinant.
First you have to find the determinant, which is
14.
14, which I don't
divide by it,
Why are we using 14?
Oh, and then do the swap.
and then you do a swap,
6, 3, -2.
and then you put negatives on those guys.
Ever remember this if we define
So what do we get? 1/14 times
I know what it is.
30 minus 16.
30 minus
1.
14.
Oh, 114 times 14 is 1.
And 24 minus 10.
14.
How
Still.
boring.
It's almost like you learned it this way.
So what does this tell me? It tells me that the projection, so the least squares solution is this guy. So when we were trying to solve, this is called the least squares solution. But moreover, you can now tell me what is the projection of my original vector b into the column space of A.
It's that, it's A times that.
It's A times that, which means it's 1 times the first column
Plus 1 times.
plus 1 times the second
So
column.
302.
302. How can we check our work to be sure we haven't mucked it up?
Oh,
See if it
dot
solves
dot.
A.
See if,
It fits
That's
in that
perpendicular.
It makes
Not-
A equals P consistent.
See if that dotted with any vector in the column space.
no,
See if solve for.
something has to be perpendicular to something. What has to be perpendicular to what?
Oh, B minus that.
B minus that. So you're looking at the error vector,
Oh, that's right.
right? You've got your column space you've got your B, you've got your alleged projection, it's the error vector that you want to be orthogonal to the subspace. So let's just double check that. What is B minus P in our case? You're too fast for me, Allison. What was it?
-2, -1, 3.
Okay. Is that perp to the column space?
Yes. Yeah.
Yes.
Otherwise, we'd be in serious trouble.
Otherwise, that doesn't guarantee that we're correct. On the other hand, I didn't stop to say it. If you know that P really is in the column space, and you know this is perpendicular to it, I said there was a unique P. We didn't prove that P was unique. But let's stop and say that before I do the rest of the other computation. Why is P unique? I said it was in the definition, but I cheated.
Because if P wasn't P, then it would be greater.
But you can have magnitudes of the same. So it doesn't prove it.
Is it?
So why couldn't we have, let's see if I can draw a picture here.
Because we're. It's got to do with dimensions.
Could you,
P sub prime, why couldn't you have two different vectors that both had the property that B minus those guys are both perpendicular?
Because
Did you
then
wanna talk
those
about-
would that would make a plane,
did you talk about coordinates with respect to?
right? I mean that would become a plane that would have that property. If you have two vectors that have that property.
Because the perpendicular vectors coming out of them would be parallel and they would never intersect at your point.
No, they don't have to be parallel because this could be 2 dimensions inside 12.
Oh, okay.
So they could still both be in the perp, couldn't they?
Yeah. But it's not. Would you want to talk about, like,
But you're sort of on the right track.
sort of?
Tell me about this triangle here.
Yes.
That's in a plane, is it not?
Yes.
Mm-hmm.
Yeah.
Oh, and we did this already.
We did this. This is a right angle, and this is a right angle.
That's not a triangle.
So Matthias said they would have to be parallel, well, he was right.
Okay.
They're both in the perp, but they would in fact have to both be orthogonal to this particular vector P prime minus P here.
Yeah.
So in that plane, they would end up being parallel, which can't happen. Right? You can't have a triangle with two parallel sides.
You can come pretty close though.
Can you do something with projector geometry?
As far as the sun's concerned, you can't.
So anyway, it really is unique. That's all the
Satellite
probability
is
set.
gonna be parabolic.
All right, let's do the second. Let's do the least squares fit to those data points.
Two rays coming in the same satellite in parallel.
So the fitting the data points. And by the way, if you've never taken high school stat or stat here where you do these sorts of things, you can fit multivariate things. It doesn't have to be a line in a plane. You could have lots of independent variables. You could do exponential fits and logarithmic fits. It doesn't have to, you still will get systems of linear equations. You'll just have more than two columns in your matrix. So again, can you now tell me what the normal equations are going to be without my writing everything out? What's A? Here's A now. Here's B. What's A transpose A?
Oh, broken.
Wait, 4 plus 2 plus.
What did you say?
5, 7?
No. Wait, are you doing
A transpose.
A transpose A or are you doing A transpose B?
A transpose.
A transpose B. 3 plus 2 is 5.
I'm getting
what, 9, 4,
That's
And
7.
5, 6, 7, okay. What's A transpose A?
9, 4, and
9.
2, and 2, and 1. So 9, 1, 1, 4.
You don't sound very convincing.
I'm just making it up as I go along, so.
Is Dan right?
Yeah.
I think so. It seems okay. We'll trust it.
Yes.
So we're dotting the columns with one another
No, 1, 1, 1.
and
1.
themselves, right?
1,
Are we okay?
Yes.
7.
Negative 2 squared plus 2 squared is 8 plus 1 squared is 9, etc. All right, so what are our A bar and C bar?
B bar.
No, they're not B. That's why I used A and C, and I didn't want any B's here. I want the inverse of this. 1 over,
Which is
what's 9 times
35.
4?
1 over 27.
12, 1 over 12. Wait, 9 times 4? 35.
I
What's 4 times 9?
I don't know what 4 times 9 is.
All right, I don't think this one comes out quite as pretty.
So pretty. 13.
Yeah, 13.
13. And 58.
58.
658?
And I don't even think fractions can be reduced here. So what does that look like? 13 35ths. Those of you who like decimals might even want to get out a calculator. This is A bar. This is C bar. So it's got slope
It's near 1/3.
bigger than a third. Does anybody have a calculator? I guess it doesn't matter, but if you did, we could get decimals. And this thing is about 1.5. A little bigger than 1.5. So does that look realistic?
Yeah, that makes sense.
Yeah.
So we're saying the y-intercept is a little bit more than 1.5, and the slope is between 1/3 and 1/2. So the line I drew in there is approximately right. What are the decimals?
0.37 is your slope,
3.7, okay.
and just about 1 2/3, so 1.66.
Well, so my eyeballing isn't quite right. I failed.
Better luck next year.
All right. Now, I don't know if you have been taught this or if you've ever noticed it, but it was only after I started teaching linear algebra that I actually noticed this. You're minimizing, so we'll go through the calculus on Wednesday. You're minimizing the sum of the squares. When you do this projection onto the column space, you're minimizing the sum of the squares of these distances.
Oh, yeah. Yeah.
That's what's going on with that projection. What is it saying about the actual signed differences here?
Close to 0.
They add up to 0. How many of you knew that? So, cool observation here. When you do the data fit, if you say, if you look at the error vector, which is b minus p, and you think of it as a vector with components, I'm claiming that for the least squares solution, so this is one thing you can check when you draw the picture and eyeball it, do those actually add up algebraically to 0?
Interesting.
Well, my picture's a little off, actually, which is good because we already agreed that my y-intercept is too small. So why is this true? Hint. What do you do with a vector if you want to add up its entries? Dot it with what something?
The identity.
No, the 1, 1, 1, 1.
You're dotting the vector with 1, 1, 1, 1, 1, 1, 1, 1. Why is that 0?
Because there's in the columns.
Oh.
And why is 1, 1, 1, 1, 1, 1 in the column space, Cal?
Because it's one of the columns.
Well,
I see that now.
but where did that come from? It came from having
A constant.
Oh,
the constants having all appearing in the equation with coefficient 1.
Wow.
So this follows because b minus p is in the perp of the column space, and 1, 1, 1, 1, 1 is in the column space. So it's an immediate consequence of the geometry, of the algebraic sentence. And there are generalizations of this to higher dimensional things too.